do I need this?
So वरना basic level भी drawing it won't make sense.
So what I need to do then again is that, okay, apply star. Okay, let's not complicate our life for the moment. Let's apply directly star on this expression. So if I'll apply the star on this expression, what I'm going to get? F1 star theta 1, F2 star theta 2. It's just labor actually, you can do it for yourself. Star theta 3 actually. So this would be same as F1
theta 2 with
so this would be theta 2 wedge theta 3 minus F2 theta 1 wedge theta 3 plus F3 and theta 1 wedge theta 2 wedge. Okay, so you get it. Next I would like to apply D on it. Okay. I can, by the way, apply D on this directly. Okay. So if I apply D on it, so what is it going to look like?
Partial F1 by partial theta 1.
Okay, so I can't write partial F1 by partial theta 1 because theta is co-frame. So I have to first express these in the terms of the coordinates. And these Fi's are depending on what Ui's actually. So if I want to operate D on them, then first I need to express everything in the terms of U. So what would be the U form of this? In other words, what is theta 2? So theta 2 is H2 du2 and theta 3 is H3 du3 and is it this or other way around? So I'm going to have a reciprocal here.
no sir.
So this is correct.
Yes.
So the theta 2 wedge theta 3 is going to be H2 H3 du2 wedge du3.
H2, H3, F1.
So this would be H2 H3 F1 du2 wedge du3 minus okay, so H1 H3 F2 du1 wedge du3 plus H1 H2 F3 and du1 wedge du2. And now I can apply D on both sides. So if I apply D on both sides, okay, so what I'm going to get? So H2 and H3 are like numbers, so they're going to stay same. So I have to do what? Partial F1 by partial U1. I have to also do it through U2 and U3, but those will be 0. And you're going to get du1 wedge du2 wedge du3. Okay? Minus, okay? It's just laborious calculations, nothing else. H1 H3 partial F2 by partial U2 and you're going to have du2 wedge du1 wedge du3. I can put a plus here and I can switch it already. So du1 du2 du3. So the third plus I'm writing it here.
H1, H2.
Okay.
H1, H2.
So this would be H1 H2
partial F2, F3 by U3.
partial F3 by
D
U3, and you're going to have a du3 wedge
U1,
du wedge du2 wedge. Okay? And I can switch it twice actually, so like once the sign would change and then I can switch again and sign would change, so you're going to get plus h1 h2 partial f3 by partial u3, and you have again du1 du2 and wedge du3, so you get this. So almost done. I need to again apply star on these axes. So this will be the last step. Okay?
yes sir.
Alright, so if I will apply star on this expression,
Star D star.
by the way, I can do one thing, I can combine these three expressions, I can put them in a single bracket because you know all these are same. Okay, so it's a kind of a one single tree form. So star B star F would be what?
H2 H3
So let's write D star F first and then. So can I write this as partial by partial U1 H2 H3 F1. I should even put it to make it compact actually because it's easy to plus partial U2 H1 H3 and
F2
F2 plus partial by partial U3 and H1 H2 and F3, and everything is wedged with du1 wedge, du2 wedge, du3. Okay. Now if I apply star on this, what I'm gonna get? I'm gonna get star on
the coefficient this would end up
the
being
last part. Huh?
Sign we did it before.
So what would be this star operated onto this? What would be the star operated onto this? So this would be what? Okay? This would be what? So if this is 1, you get what? So you get the same expression without this.
Sir, but this is
Uh-huh.
so why do you
ये हमने बचपन में पढ़ा था. We have done it. We have done. So how can I have a star of du1? Okay, here du2 wedge, du2 wedge. Okay, remember du3. If I apply definition, I'm gonna get a star epsilon. Okay, and you're gonna get all. So you're gonna have 1 over 3 minus 3 factorial. Okay, so I'm assuming that we remember the form. And if you don't remember my sympathies are with you. Okay, so you have 1 over 3 factorial. So I'm gonna have a Levi-Civita symbol with 3 indices above and nothing here, gone. And what you're gonna get here actually? So nothing. So you're not going to have anything here actually, okay? So what you're going to get? And what is this Levi-Civita symbol? So that's an even transposition. So that's 1. So you get a 1 actually pure. Okay? Alright, so this is the expression for the divergence. So this is my, essentially I can say,
Sir,
the divergence
जब हम चेंज करते हैं तब हम थीटा वाई की फॉर्म में करते हैं.
I can write it in the form of a theta.
So that way you will get 1 over h1 h2 h3.
Oh yes. Yes. So, oh yes. This is good. This is a very good point. So du1 wedge, you have du2 wedge du3, but I know that du1 wedge, du2 wedge, du3 is gonna be what?
1 over
1 over h1, h2, h3,
theta.
and theta 1 wedge, theta 2 wedge, theta 3. And then if I apply star on this, I'm going to have a star on this, and this would be 1. You're going to get h1, h2, h3. So therefore, you will have the same quantity, h2, h3, multiplied by the expression that you have above it. So this would be the expression for the divergence. Okay? So what does this divergence is telling you? This expression, if you put it here. So this is the divergence of a vector field, but in curvilinear coordinates actually. So in other words, if a vector field is defined on a sphere actually, okay, imagine that something is something is curling or something is, so it's like a vector field is diverging out but on a sphere actually, and you want to compute its measure, okay, then the best would be to apply or measure it in the terms of spherical coordinates rather than what you call Euclidean coordinates. Okay, Euclidean coordinates for work for us. For example, when we measure flow here, okay, on Earth actually, we don't use spherical coordinates. Why? Because
Locally.
it's Euclidean actually. Locally it's Euclidean. But you can be more precise by using this. Are you getting the point? This will be the divergence. So in order to have an explicit expression for the divergence, for example, in spherical coordinates, what do you need to do? So you just need to substitute these h1 and h2 and h3, which you can get from the metric, because these are the square root of metric component actually. Okay, so you can substitute it there. Imagine that the values of f1, f2 and f3 is given to you. You can get an explicit expression for divergence, but in the polar coordinates. So these are the small things. It's almost become a tutorial. Okay. These are some of the small things that you have to learn. Okay, I have left curl basically. Okay. You must practice on this, and maybe you can get some other quantity which you have to express it in the terms of curvilinear coordinates. Okay. Maybe in your assignment or in your exercise or in your exam cycle. Okay. So this is what that we have to do. So this is end of the story for this section. So what was the moral of this section? The moral, the end result of this section is that how you can express things in curvilinear coordinates, and specifically how you can express these fundamental tools of curl gradient divergence in curvilinear coordinates. The next thing that I would like to do so-called covariant derivative. What is covariant derivative? First of all, covariant derivative generalizes the notion of directional derivative. We know that directional derivative is what? Directional derivative, we compute it, so it's like we want to compute the change in a particular scalar field, but in a particular direction of a vector actually. Okay, but I'm computing the change in a scalar field. I can ask a question: can I compute the change in vector field in the direction of another vector field actually? So that would be kind of generalizing this directional derivative thing actually. Are you getting the point? So what we are interested in, so I am interested in, and the way to do it is covariant derivative basically. So what the covariant derivative is essentially, the covariant derivative is that how you can compute the derivative of a vector field in the direction of another vector field actually. Okay? So it's a kind of a directional derivative, but computing the directional derivative of one vector field in the terms of in the direction of other vector fields. So that's what essentially is the basic idea. Okay. I would like to point out here that a typical introduction of the covariant derivatives always starts from the point that if you are in Rn, everything is easy actually. It's pretty easy. We're going to see that it's pretty easy to compute covariant derivative. Okay, I can easily define that what is the meaning of computing derivative of one vector field in the direction of other vector field. Okay, but if you are on an abstract manifold, so in Rn it's easy. Okay, but if you are on an abstract manifold, that's very difficult actually. So you have to use some trickery to define it actually. So it would be, so you can define it, the covariant derivative, we can define covariant derivative onto manifold, but we have to define it cleverly. Okay? So it's going to be a bit analog what we are going to do now. Why it's difficult to define it on abstract manifold? Because you have to keep one thing in head that so the abstract manifold is basically a topological space. Okay? So it's a topological space roughly in which every point has a neighborhood, which is homomorphic to an open subset of Rn actually. Okay, so that's what is what we call at least n-dimensional manifold is basically. Okay. So if I have an abstract manifold, I'm talking about a topological space. And in order to define derivative, any kind of derivative, no matter what derivative you have to compute a difference actually. Okay, so it's like I'm at a particular position, I'm moved ahead, and I need to compute a change actually. Okay. The question is that on abstract manifold, you don't have a notion of algebra, so you can't add and subtract things there actually. So topology does not allow you to do algebra. Okay, you can have topological vector spaces like Rn. So in other words, you can have spaces in which you have a topology and you can do algebra. So there it's pretty easy to define things because then you can define, increments and all these things. Are you getting the point?
Yes, sir.
So in Rn it's easy to define because Rn we know we have a topology. We can have topologies, but we also have algebra. So in other words, we can add two vectors or subtract two vectors actually. Are you getting the point? So if you want to, for example, define a derivative, a kind of a derivative, you have to define, or you can define it by taking the difference or taking the increments actually. So increments make sense in Rn actually. If you are in Rn, it's not a big deal. But in abstract space, you can't talk about differences actually. Why? Because
why can't we have algebra there?
I'm sorry.
Why can't we have algebra in abstract manifolds?
In abstract manifolds, I mean, if you are going to have, for example, a kind of algebra there, then that will be not much that abstract object because then that will become a topological vector space actually. So in other words, the trick is this: in order to define the derivative on an abstract manifold, can I define it without using the algebra? The answer is yes, you can do it actually using some tricks. Okay, using some tricks. But we are not going to, get into that definition actually. Okay, so we are going to define the derivative. Okay, using algebra actually. Okay, using algebra. So that's what is the key thing to keep in our head actually. Okay. That on an abstract manifold, covariant derivative is a pretty complicated object, but in our end we are happy. It's not good. It's going to be ultimate. You're going to see it's the ordinary derivative. It's not that difficult. So let's get into what do we mean by covariant derivative. So here's the definition. Imagine I have a vector field in Rn, so let x be an arbitrary, that's an arbitrary vector field in Rn. Okay. We have to keep one thing in head, the definition that I am going to propose now is going to generalize our previous definition of directional derivative. Okay? So it's going to be a generalization. So see, what properties a derivative must have actually? So it should be something linear, should linearly act on things. That's the first thing that we should have. And so the linearity is the essential part, should be there actually. Okay. So in other words, if I want to define, for example, an operator which can kind of serve as a derivative for us. So let me define a map del x bar. I'm putting a bar so that you can differentiate it from the gradient actually. Okay. So I'm defining this del x bar. So it's a map from the tangent bundle of Rn into the tangent bundle of Rn. So this map is called a connection. Okay. Or some people like to call it causal connection. Koszul connection. Okay. If it satisfies falling, if falling are satisfied, if falling are satisfied. Okay. So what property should it have? So it must be linear with respect to the vectors on which this, this operator is operating. So in other words, if I have del x of, some vector field y1 plus y2, it should give you del x y1 plus del x y2. Okay. And if the del x is operating onto some fy, okay, it's operating onto some fy, and what output you must expect? So it should give you xf, in other words, the directional derivative. Okay. So in other words, del x operated onto, so it would be kind of a product rule actually, roughly a product rule. So del x operated onto f multiplied by y plus f multiplied by del x operated onto y. But if the del x is operated onto f, that is classical. You know, the classical directional derivative. And how do I represent classical directional derivative? So I use this notation. Okay? Y plus f del x. By the way, if you remember in the first chapter, we gave such kind of creature a name. In other words, something that satisfies these two properties, we gave them a name. And what was that? Linear derivations. Okay. So in other words, this connection or the causal connection must be a linear derivation. So that's a linear derivation. And the third property that it must satisfy is that, okay, so it's linear, so roughly it's linear with respect to, it's a linear derivation with respect to the vector fields on which it is operating, but I want it linear also to be with respect to the directions in which you are computing the derivative. Okay, it's a bit abstract thing, you can solve it. So that's when I am operating del x operating onto y1, what does it mean? So I am computing the directional derivative of y1 but in the direction of x actually. Okay? So I want this operator not only to be linear with respect to these components, but I want also them to linear with respect to this component as well. So what do I mean by that? So in other words, if I am computing the directional derivative of y, okay, but in the direction, not in the direction of x, but fx actually, where f is some scalar field. Okay? Then what output I must expect actually? That it should be f multiplied by the directional derivative of y. Directional derivative, covariant derivative. Are you getting the point? And what should I have the fourth property? That if I have, I'm computing the directional derivative, okay, but in the direction of sum of two vectors, then it should give you what? Del x1
of y
plus
del x2 of
del x2 of y. Is it making sense? Okay. You have to keep one thing. Any map which satisfies these four properties would be a connection. Any map. Okay, so that's an abstract definition actually. If you have a map which satisfies these four conditions, it's a connection actually, a causal connection. Any map. What would be the example of this? So my claim is that this species is an excellent thing that kind of allows me to compute, that kind of generalizes the classical notion of directional derivative. By the way, I must mention that these x, x1, x2, y, y1, y2, they all are vector fields. These all are vector fields. And f is a C infinity map. There's a proposition. There's a proposition. In Rn, I can give you an example of this particular map. Can be other, but I can give you one example. So here's a quick proposition. I'm not going to prove it You have to verify it for yourself. It says that imagine I have a vector field y whose components are fi partial by partial xi. Okay? Where these fi's are smooth C infinity functions. Where these fi's are C infinity functions on R. So let y be